A funeral, a graveyard, an ending written years before the reef was finished. That was the story most people absorbed from a single dramatic season of footage. This is the fuller version of that story, built from field data, not headlines. In 2016, scientists flew over the Great Barrier Reef with cameras rolling. Mile after mile of coral had turned completely white below them. The footage spread across news networks within a matter of days. Reporters called it a funeral for the largest reef on Earth. Some marine biologists went even further than those grim headlines. They said the reef was already gone in every practical sense. A structure stretching 2,000 kilometers became a single dark statistic overnight. Fishermen along the Queensland coast stopped speaking about the reef normally. Divers who had worked these waters for 30 years described graveyards below. Tour operators watched entire seasons of bookings cancel within one news cycle. Insurance companies adjusted their risk models for the whole region soon after. And yet, in the years right after that funeral, something strange happened. The Great Barrier Reef is not one continuous single reef structure. It is closer to 3,000 separate reefs strung along the coastline. Some sections stretch for many kilometers without a single visible break. Others are barely larger than a suburban parking lot in size. Together they form the largest living structure found anywhere on the planet. Astronauts have photographed it clearly from low Earth orbit. For millions of years, this system survived ice ages and rising seas. It survived cyclones strong enough to flatten entire coastal towns nearby. What it had never faced quite like this was sustained, relentless heat. Heat stacked on heat, summer after summer, with no recovery window left. Coral bleaching sounds like a mild, almost cosmetic form of damage. It is nothing close to mild once you understand the mechanism. When ocean temperatures climb above their normal seasonal range, coral reacts fast. Coral polyps expel the tiny algae living inside their own tissue. That algae supplies both the coral's color and its main food source. Without it, coral turns stark white and begins slowly starving to death. Some bleached coral recovers if water temperatures drop back down quickly enough. Plenty of coral colonies never get that narrow window of time. The 2016 event alone killed roughly a third of shallow water coral. A second bleaching event struck again the very following year. Scientists had never before documented two bleaching events landing back to back. They gave this new pattern a blunt working name. They called it back-to-back bleaching, and the term stuck immediately. Recovery periods that once lasted a full decade suddenly disappeared entirely. Reefs barely had months to rebuild before the next heat wave arrived. But heat was never the only serious threat facing this reef. Long before bleaching made international news, another killer moved through the coral. It worked slowly, one bite at a time, section by section. It stayed invisible to satellites and largely ignored by passing tourists. It carried toxic spines and one of the largest appetites in the ocean. Its name was the crown-of-thorns starfish, already old news to marine biologists. This particular starfish had been devastating reefs for roughly 60 years. Most casual visitors to the reef had never even heard its name. A single adult crown-of-thorns starfish can grow larger than a dinner plate. It carries up to 21 arms, each one lined with venomous spines. Underneath its body, it hides a stomach it can push outward. It presses that stomach directly against living coral tissue in order to feed. One adult starfish can strip more than 10 square meters of coral bare. It manages that much damage in roughly a single feeding season. That level of destruction is bad, even at ordinary scattered population densities. The real disaster starts when populations explode into what scientists call an outbreak. Official records show 4 major crown-of-thorns outbreaks on this reef since the 1960s. Each outbreak can drag on for years, sometimes past a full decade. During an active outbreak, starfish densities can climb several hundred times normal levels. Reef sections that took centuries to build can vanish within a few outbreak cycles. Researchers eventually ranked this threat against every other force damaging the reef system. Only mass coral bleaching and severe cyclones scored higher on that particular list. A slow-moving, spiny, unglamorous starfish was rivaling climate change on its own terms. For decades, marine biologists searched hard for any natural check on this animal. In the 1960s, researchers finally identified exactly one reliable natural predator for it. It was a massive sea snail called the giant triton. Its shell alone could grow to roughly half a meter long. Tritons inject paralyzing saliva into a starfish before slowly feeding on it, but triton shells were also heavily prized by shell collectors worldwide. Decades of shell collecting had already thinned triton numbers across huge reef stretches. One known predator, slowly disappearing, left the starfish almost nothing standing in its way. Governments naturally tried blunt, direct solutions to this outbreak problem first. Divers were sent out with chemical injection guns to kill starfish individually. It worked, locally, in small patches, for relatively short stretches of time, but a single outbreak could spawn millions of larvae in one season. No team of divers could physically out-inject a flood on that scale. Meanwhile, researchers kept returning to one older, strangely neglected question worth asking. If one snail alone could not realistically save the reef, what else was already eating these starfish out there? That specific question sat mostly unanswered for roughly another 50 years. Then, in the early 2000s, Australia made an unrelated policy decision. In 2004, regulators redrew the entire zoning map of the marine park. They expanded no-take zones, where all fishing was strictly banned, considerably wider. Those protected zones eventually covered close to a third of the entire park. The stated goal at the time was ordinary, straightforward reef conservation policy. Protect fish populations broadly, protect biodiversity generally, and let damaged reefs recover. Nobody in that policy room was designing a weapon against crown-of-thorns starfish, but that is precisely what this rezoning decision became over time. Inside these new no-take zones, heavily fished species began bouncing back fast. Red-throat emperor and spangled emperor grew larger where fishing boats could not reach. Stripy snapper started forming denser, more visible schools across protected reef flats. Coral trout, among the most sought-after fish in the entire commercial fishery, multiplied fastest of all. None of these fish were specifically bred or trained for any job. They were simply doing what predatory reef fish have always naturally done, hunting anything soft enough nearby to eat, with no plan behind it. It turned out crown-of-thorns starfish, especially in their younger stages, qualified perfectly as prey. Researchers eventually identified close to 100 reef species that feed on starfish. 80 of those recorded predators were fish, many with no fearsome reputation whatsoever. Red-throat emperor and spangled emperor stood out clearly as two of the strongest links. Wherever these particular fish thrived, local starfish outbreaks measurably shrank in scale. A built-in biological check had been sitting there completely unnoticed the entire time. In 2021, a team led by Ames ecologist Frederica Kroon put a number on this. Her team compared reef sections open to fishing against fully protected ones. On the closed, protected reefs, predator fish biomass measured up to twice as high. Crown-of-thorns starfish densities on those same reefs measured nearly 3 times lower overall. That kind of gap did not look like coincidence once charted side by side. 30 years of Queensland fisheries harvest records backed up the same pattern independently. Wherever predator fish were pulled steadily out of the water, hungry starfish moved back in. A separate modeling study, led by CSIRO researcher Scott Condy, pushed the analysis further. His team simulated what likely would have happened without the 2004 rezoning decision. In that alternate scenario, predatory fish populations kept declining under continued fishing pressure. Crown-of-thorns outbreaks inside that model became far more frequent and much harder to control. Coral cover kept falling with no meaningful natural break left to slow it. Condy described the rezoning as averting a genuine, near-catastrophic ecological tipping point. A decision made for entirely unrelated reasons had rewritten this reef's future outcome. None of this erased the very real damage already caused by warming ocean temperatures. Bleaching events kept arriving through 2020 and again through 2022, hitting different reef sections. But the northern and central sections of the reef told a different story. By 2022, researchers at the Australian Institute of Marine Science recorded strong coral cover figures. It was the highest coral cover measured in those regions across 36 years of monitoring. Reef sections written off as lost less than a decade earlier were visibly rebuilding themselves. Fish that nobody had previously considered heroes turned out to be part of the reason. It is worth being clear about exactly what this recovery does and does not mean. The Great Barrier Reef is not fully healed, and no serious researcher claims otherwise. Southern sections of the reef still lag noticeably behind the recovery seen further north. Crown-of-thorns outbreaks have not disappeared, and a fresh cycle was already underway. Ocean temperatures keep rising, and future bleaching events remain a near certainty going forward. This reef's comeback is real, but it also remains fragile and entirely conditional. What changed this trajectory was never one single dramatic rescue operation. Nobody lowered an expensive piece of machinery into the water to fix coral. Regulators simply redrew a few lines on a map for unrelated reasons. Fish that biologists already knew well simply got room to keep doing their job. Red-throat emperor never knew it was technically saving anything at all out there. It was just hunting the same way it always had, unbothered. Marine parks worldwide are still frequently debated as painful economic sacrifices for coastal towns. Fishing communities near the Great Barrier Reef gave up ground in 2004. They lost access to a third of their traditional fishing grounds. That decision was unpopular at the time among people who fished those waters professionally. 2 decades later, the accumulated data suggests that sacrifice paid for something almost nobody predicted: a measurably healthier reef, and eventually a fishery holding more fish than before the closures began. Scientists are now citing this specific case to argue for similar zoning elsewhere across the Indo-Pacific. Coral reefs from the Philippines to the Maldives face this same starfish threat. Many of them carry far weaker fish protections. Predator fish suppress crown-of-thorns outbreaks here on the Great Barrier Reef. Researchers argue that same logic should hold elsewhere too. Protecting ordinary fish populations, in other words, might be a cheap tool. It could help protect coral reefs broadly. It requires no expensive new technology and no complicated international funding campaign to implement. It simply requires leaving enough fish alone, in enough specific places, for long enough. The Great Barrier Reef was declared dead in headlines across the world less than a decade ago. Divers described graveyards on camera, and scientists described a system past saving. That grim story mostly ended there for most viewers, but underwater, away from any camera crew, an ordinary reef fish kept doing its usual job. It stayed unbothered by the headlines. It hunted juvenile starfish steadily, catching them before they could grow large enough to strip a reef bare. Multiply that single fish by thousands, spread across thousands of reefs, sustained over 20 years, the reef system started writing a different ending. Nobody scripted that ending inside any policy meeting held back in 2004. There is a broader lesson buried inside this particular story. It reaches well beyond a single reef or a single starfish species. Ecosystems rarely collapse or recover because of one single isolated cause acting alone in a vacuum. The Great Barrier Reef nearly lost its coral to 2 threats at once: heat stress and an unchecked predator. It began recovering, at least in part, because one of those problems got solved first, through an unrelated policy. Nobody needed to invent some clever new way to directly stop crown-of-thorns starfish outbreaks by force. They only needed to stop removing the ordinary predator fish. Those fish had already been stopping the outbreaks all along. Today, researchers keep tracking emperor and snapper populations across the reef's marine park zones. Every fresh survey adds another data point to an argument that keeps growing stronger with time. Reefs holding healthy predator fish populations consistently show fewer starfish and noticeably more living coral cover. Reefs stripped bare of those same predator fish keep sliding back toward familiar outbreak conditions. That kind of consistency across different years, regions, and research teams is rare in ecology. None of this guarantees the Great Barrier Reef survives the coming decades completely unchanged from today. Warmer oceans remain, by a wide margin, the single largest long-term threat this reef will ever face. Fish alone cannot lower rising sea temperatures, and no zoning map can undo a severe heat wave. But fish can buy valuable time, reduce one major compounding stressor, and give damaged coral room to regrow. This reef system is already stretched thin by climate change. that small margin matters more than it first appears. Sometimes survival is not one single dramatic miracle happening all at once. It is one specific threat removed, just long enough for everything else nearby to stabilize. The next time somebody repeats that grim 2016 headline, remember this: there is a quieter answer waiting somewhere underwater right now. It is swimming past old bleached coral skeletons in loose, ordinary, unremarkable fish schools without any fanfare whatsoever. It carries no name recognition and no viral headline. It has no idea that it changed anything at all. It is simply an ordinary emperor fish doing what emperor fish have always done, one hungry starfish at a time. Against every confident prediction and every grim headline written in 2016, that ordinary behavior proved everyone wrong in the end. Field researchers spend weeks at a time living aboard small survey boats near these reefs. They swim fixed transect lines, counting every fish and every starfish they pass. Each survey diver carries a slate, a pencil, and an underwater camera rig. The work is slow, repetitive, and almost never featured on television at all. Nobody films these divers for a dramatic documentary about saving the ocean, and yet this exact data eventually built the entire scientific case behind this story. The Australian Institute of Marine Science has been running these surveys since the 1980s. That long baseline is precisely why the 2022 coral figures carried real scientific weight. Researchers were not guessing about recovery based on a single hopeful season. They were comparing fresh numbers against 36 years of consistent, methodical monitoring data. Without that decades-long baseline, nobody could have proven anything beyond simple coincidence or luck. Long-term monitoring rarely makes headlines, yet it is what makes discoveries provable. Coral trout deserves particular attention in this story, given how heavily it gets fished. It is one of the most popular eating fish sold across Queensland seafood markets. Before 2004, coral trout numbers on many reefs were noticeably thin from fishing pressure. Inside the new no-take zones, coral trout numbers rebounded faster than almost any other species tracked. Bigger, more numerous coral trout meant more juvenile starfish being eaten before reaching adulthood. A fish prized mainly for dinner plates turned out to be guarding the reef. Red-throat emperor tells a similar story, though it draws far less public attention overall. It is a mid-sized reef fish, silvery, with a faint reddish tinge near its throat. Commercial fishers have targeted it for decades because of its firm, mild-tasting flesh. Recreational anglers also favor it, adding extra pressure on populations near popular fishing grounds. Inside protected zones, red-throat emperor numbers climbed steadily once that fishing pressure was removed. Nobody marketed this fish as an ocean hero, yet the data clearly says otherwise. Spangled emperor rounds out this trio of unlikely coral defenders quite well. It grows larger than red-throat emperor and hunts across slightly deeper reef terrain. Juvenile crown-of-thorns starfish settle in these same depths shortly after their larval stage ends. That overlap in habitat gave spangled emperor repeated opportunities to intercept starfish early. Early interception matters enormously, since a starfish caught small never grows into a reef-eating adult. Timing, in this story, turned out to matter just as much as raw appetite. Stripy snapper adds one more layer to this picture, operating in tighter, busier schools. These fish patrol shallow reef flats where juvenile starfish often settle after spawning events. Their schooling behavior lets them cover far more reef area per day than solitary hunters. Researchers noted denser stripy snapper schools directly correlated with lower juvenile starfish survival rates nearby. None of these fish species coordinated with each other in any conscious sense whatsoever. Their combined, overlapping hunting ranges simply happened to blanket the reef in coverage. None of this recovery would have been visible without the 2021 Croon study connecting the dots. Before that paper, these fish were studied mostly as commercial stock, not reef guardians. The study reframed decades of fisheries data through an entirely different ecological lens. Numbers that fisheries managers had tracked for stock assessments suddenly told a conservation story too. Sometimes the most important discovery is a new question asked of old data, not new data itself. Critics of marine park expansions often argue that closures simply push fishing pressure elsewhere. That criticism carries real weight and deserves honest consideration rather than dismissal. Some fishing effort near the Great Barrier Reef almost certainly did shift toward open zones, but total fish biomass across the wider region still climbed following the 2004 rezoning overall. That regional increase suggests displaced fishing pressure did not simply cancel out the protective effect. The trade-offs here were real, even if the overall regional outcome favored conservation. Local fishing operators eventually noticed a secondary benefit few had expected. Larger fish inside protected zones eventually spilled over into adjacent open waters. Fisheries scientists call this pattern spillover, documented across several marine reserves worldwide. It softened the economic blow, even without replacing the grounds lost outright. A policy built for conservation ended up supporting the very industry it restricted. Tourism operators near the reef eventually noticed their own version of this recovery. Dive shops began advertising healthy coral in the exact areas hit hardest by 2016 bleaching. Visitors who had read that funeral headline arrived expecting to see only bleached rubble. Instead, many found dense schools of emperor and snapper weaving through recovering coral. A grim 2016 headline was slowly being undone by ordinary tourists posting their own photos. None of this recovery erases the uncomfortable fact that outbreaks remain an active, ongoing threat today. The fourth recorded crown-of-thorns outbreak, referenced earlier, was technically still unfolding as recent studies were published. Researchers continue injecting individual starfish by hand on reefs where predator fish numbers stay low. That manual culling program still costs Australian taxpayers millions of dollars annually to sustain. Predator fish reduce the scale of outbreaks, but they have not eliminated outbreaks entirely on their own. The story here is one of a threat meaningfully reduced, not a threat fully solved. Climate projections for the Great Barrier Reef remain hard reading for anyone following this story. Even optimistic emission scenarios suggest further mass bleaching events sometime within the next 2 decades. Coral recovery, however encouraging, cannot outrun ocean warming if that warming keeps accelerating unchecked. Scientists studying this reef are careful never to frame 2022's numbers as a final victory. They describe it instead as evidence that targeted interventions can buy meaningful, measurable time. Time, in a warming ocean, is not a small thing to secure. Red-throat emperor does not know its recovery became a scientific case study. Decisions made in fisheries offices in Brisbane echo directly through coral ecosystems offshore. A permit granted or denied changes fish density, which changes starfish survival, which changes coral cover. Ecology rarely respects the boundaries humans draw between departments, budgets, and headlines. Back on the reef itself, none of these details register to the fish involved at all. A red-throat emperor patrolling a reef flat has no awareness of any policy debate. It simply responds to hunger, habitat, and whatever prey happens to be nearby. Every ecological outcome described in this story emerged from thousands of small, unconscious decisions like that one. No fish understood the stakes, and none of them needed to in order to matter. That is, in the end, the quiet irony sitting at the center of this recovery. Humans spent decades searching for a deliberate engineered solution to a devastating coral predator. The actual solution had already been swimming across these reefs the entire time, largely unnoticed. It simply needed enough water, enough protection, and enough time left alone to work. Sometimes the fix a struggling ecosystem needs is an old intervention, simply restored. The Great Barrier Reef will keep facing outbreaks, keep facing heat, and keep facing hard choices ahead. But the reef that was declared gone in 2016 is still here, still recovering, still being studied. Ordinary fish, doing ordinary things, reshaped a story that once read like an obituary. Nobody wrote that ending in a headline, a press release, or a policy briefing. The reef wrote it. One emperor fish, one stripy snapper, one saved coral colony at a time. None of this means the story ends here, on a settled, comfortable note. New surveys go out every season, and new numbers keep arriving from AIMS. Some years will bring good news, and some years almost certainly will not. Another bleaching event could arrive next summer, or the summer after that. Another outbreak could still overwhelm even a reef full of healthy predator fish. What changed in 2004
Better
was not a
odds,
guarantee,
sustained long
only a
enough,
set of better
are often
odds.
the only
Better
thing
odds,
separating recovery
sustained
from
long
collapse.
enough, are often the only thing separating recovery from collapse. That is a smaller claim than the word miracle usually implies, and a more honest one. It is also, on the evidence gathered so far, the more accurate one.